Hello everybody, welcome back one more time. We're going to look at part C this time, describing the dynamic behavior of C hat and K hat in a phase diagram. So here's the question. Whoops, forgot to put that up. And let's do it. You can just draw the phase diagram. I don't think that's super hard. My concern is for a 2-point question, whether just drawing it and saying, alright, there you go, is going to be enough to get full marks. So what I want to talk about in this video is a method for testing how we derive the phase diagram. How do we know that it goes the way it goes? What goes here, what goes here, what goes here? And you can just memorize it, but this is, I guess, the way to figure it out. So we'll start with the K hat, and the way to do it is to just test points. We'll pick two values of C hat, one greater than the other, and importantly, one will be on the K hat equilibrium schedule, and one will be off of it. So let's call this one C hat 1 and this one C hat 2. And we can compare which one is bigger than which by plugging them into the K hat equation in steady state when K hat dot equals 0. We know that K hat dot equals 0, and we know that C hat 1 is greater than C hat 2. So let's just plug them in. We have f of K hat minus K hat x plus n plus delta minus C hat 1, and then something f of K hat minus K hat x plus n plus delta minus C hat 2. So this and this are the same number, and C hat 1 is larger, so subtracting something larger will be smaller, and we'll get that, yeah, this less than inequality. Now, because C hat 1 here is on the equilibrium schedule, we can also say that this equals 0, this whole thing. So we can rewrite this as 0 is less than f of K hat minus K hat x plus n plus delta minus C hat 2. And this is actually K hat dot associated with the C hat 2. So turning that around, you get that the K hat dot at C hat 2 is greater than 0. And so what we found is that inside the K hat dot schedule, things go up, things go to the right. K hat is increasing, and outside it is decreasing. And we can do kind of a similar test for the C hat dot schedule, picking one value of K hat here, call that K hat 1, and one value of K hat here, call K hat 2. And importantly, again, they're both at the same value of C hat. And now this time we're going to plug them into this equation. So 1 over theta f prime of K hat 1 minus delta minus rho minus tau gamma is something to 1 over theta f prime of K hat 2 minus delta minus rho minus delta gamma. And here we can't do a direct comparison like we did in the K hat case because we're looking at f prime of K hat. We're not looking at K hat 1 and K hat 2 itself. So we have to think about what we know about the function f of K hat. And we don't know the specific functional form of it, but we do know that it's neoclassical, which means that f double prime of K hat is going to be less than 0. It's concave, right? So if you think about two values of K in this function, one value that's larger, so this would correspond to the larger one. We know that K hat 1 is greater than K hat 2. So the higher function, k hat 1 is actually going to have a less of a slope than k hat 2. In terms of first derivative, k hat 2 is going to be greater than k hat 1. So we can say that f prime of k hat 1 is less than f prime of k hat 2. So for our big mess up here, we just have same thing. We could just reduce that to this. So we can just write a less than here. Now, once again, we picked a point on the schedule because now we know that this whole part over here, this just equals 0. And this whole part over here, that just equals the c hat dot associated with k hat 2. So the c hat dot associated with k hat 2 is going to be greater than 0. So for points to the left, c hat is increasing. And for points to the right of the schedule, we just assume the inverse is true. You could do the test again, but I don't see why you would do that. And so there you go. That's the phase diagram derived for the Ramsey model.